So in this video, we're going to talk about how to determine a whole in a rational function. So remember the steps to factoring a polynomial? You'll always start off by looking for a GCF and then factoring it out, then check the polynomial for any special patterns. Then you're going to factor the remaining polynomial using factoring by grouping. So for example, if we want to factor 3x squared plus 12, we're going to start off by looking for a GCF. Notice that both of these terms are divisible by 3, so we're going to go ahead and factor out a 3. So that means that we're going to divide both of these terms by 3. And so we have 3 times, and then 3 and 3 cancel, so we have x squared. And then 12 divided by 3 is 4. So we have 3 times x squared plus 4, which is the factored form of this polynomial. So what if we want to factor 3x squared plus x minus 2? So remember, in this equation, we have a, and then we have b, which is our coefficient of x, and we have c, which is negative 2. Remember, we need to multiply a times c, so that is 3 times negative 2, which is negative 6. And then we need to find two factors of negative 6 that are going to add up to b, right? So they multiply to negative 6, and then they add to positive 1. So since they multiply to a negative number, we're going to need a positive factor and a negative factor. Since they add to a positive number, that means that the bigger factor is going to be positive. So our factors will be like 1 and 6. I'm going to make the smaller factor negative, and we have 2 and 3. So when we add these together, negative 1 and 6 is 5, negative 2 and 3 is 1. So that means that the factors we need are negative 2 and 3. So I'm going to use factoring by grouping. So I'm going to write 3x squared, and then I'm going to write plus 3x minus 2x minus 2. Okay, so that minus 2 and 3 came from here where I found the factors. And all I did was I said that like 1x is basically 3x minus 2x. Okay, so that's what I did. I expanded out that middle term. So what we do now is form two groups of factors, right? We have 3x squared plus 3x, and then plus we have negative 2x minus 2. So now I'm going to look for the GCF of each group. So from the first group, notice that I can factor out a 3, and I can also factor out an x, right? So I'm going to divide what remains by 3x. And then from the second group, I'm going to factor out a negative 2. So I'm going to divide both terms by negative 2. So when I do that, that first set, I'm going to have 3x times, here 3 and 3 cancel, and then x squared over x becomes just x. And then 3 and 3 cancel, and so do the x's, so we just have x plus 1. Now in my second set, so I have minus 2, and then here the negative 2 and negative 2 cancel, so I have x. And then I have negative 2 over negative 2, well, that's just going to be positive 1. So that common factor of x plus 1, I can factor that out, and then I have 3x minus 2. So that is the factored form of this polynomial expression. So now you can go ahead and pause the video and try factoring x squared plus 4x minus 12 on your own. So when you factor this, there is no a, so we're just going to go ahead and just use the negative 12. So then we're going to factor negative 12. Since 4 is positive, we're going to make the bigger factor positive. So the correct combination of factors is negative 2 and 6. So that means we have x plus 6 and x minus 2, and that is the factored form of this polynomial. So what we're going to talk about today is the wholes that some graphs of rational functions contain. Okay, so we talked about this a little last time. So remember, there's some points on rational functions where it doesn't have a value. Okay, so it'll be seen as a whole on the graph. So the whole will occur at an x value where the numerator and denominator both equal 0. Okay, and that happens when you have a common factor in the numerator and denominator. So for example, this here, this f of x, notice that if I factor the numerator, okay, the numerator is x squared minus 4. If I factor it, I have x squared minus 2 squared. So that's the difference of 2 squares, so I have x plus 2 times x minus 2. So if I write this as a product of its factors, I have x plus 2 times x minus 2 over x plus 2. Right? So notice that that x plus 2 is a common factor, okay? So I will have a whole where that x plus 2 equals 0, okay? So if I solve that for x, that means that x equals negative 2, okay? So that's where I'm going to find the whole on this function. So wholes are also known as removable discontinuities, and the reason is because if this hole was filled in, this would be a continuous function, right? So it's a removable discontinuity because like if it existed, then the function would be continuous, but it does not, right? So that's why the function has a discontinuity there. So here's how you determine wholes on rational functions. So you're going to factor the numerator and denominator and look for those common factors. The x-coordinate of the whole can be found by setting the common factor equal to 0 and solving for x. You also need to find the y-coordinate of the whole, right? Because the whole is a point, so it's going to have an x-coordinate and it's going to have a y-coordinate. The y-coordinate can be found by plugging this x value into the simplified function that exists after canceling the common factor. Then you're going to compare it with the graph. So what do I mean by the simplified function? Okay, so let's go back to this example. So the simplified function would have been if I'd canceled this common factor. Okay, so if I'd canceled that out, you can see the simplified function would have been x minus 2. Okay, so it would have said f of x equals x minus 2 because that's what I got when I canceled the common factor. So to find the y value, what I would have done is I would have gone and plugged in negative 2 into this, right? So I would have had negative 2 minus 2. So that tells me that y equals negative 4. So that means that the whole of this function would have existed at negative 2, negative 4. So now let's try a different example. Let's determine the whole of x squared plus x minus 12 over x minus 3. So you always want to start off by factoring. Okay, so we're going to factor this expression. So remember that b here is 1. So I have negative 12. I need two factors of negative 12 that are going to add up to 1. Since 12 is negative, I need a positive and a negative factor. Since 1 is positive, I'm going to make my bigger factor positive. So I have 1 and 12. And then I have 2 and 6, 3 and 4. And that's all my factors. So these two add up to 11. And then we have 4, and then we have 1. So negative 3 and 4 is the correct combination. So if I write this in factored form, it's going to be x minus 3 times x plus 4. Okay, so f of x, if I write it in factored form, is going to be x minus 3 times x plus 4 over x minus 3. Okay, so we're going to find the common factor. Notice that the common factor is x minus 3. So we can figure out the x-coordinate of the whole. So we have x minus 3 equals 0. So if we solve that, that tells us that x equals 3. Well, to find the simplified function, right, to find the y-coordinate, we need to simplify this function. So we're going to cancel the common factor. And so that gives us x plus 4. So now I'm going to go to x plus 4. I'm going to plug in x equals 3. So that's 3 plus 4, which equals 7. So that means that the whole is going to occur at 3, 7, right? So that's where I'm saying that the whole occurs. So you can verify this by looking at the graph. So if you graph this function, you'll notice that it does in fact have the whole right here that is located at 3, 7. Remember, if you're in Desmos, you'll have to click on that point to see that it's a discontinuity. So let's determine the whole of this function, okay? So it says whole or wholes because some functions may have more than one whole. So it just depends on how many common factors you have. So here it's nice because this function's already factored for us, right? I'm just going to write this a little bit more factored. I'm going to write this as 2 times x, okay? Because x squared is x times x. And then we have x minus 2 times x plus 1 over x times x plus 1. So I'm going to look for the common factors. So notice I have an x and an x in the numerator and denominator, and I have an x plus 1 and an x plus 1 in the numerator and denominator. Okay, so those are our common factors. So we're going to set each common factor equal to 0. So we have x equals 0, or we have x plus 1 equals 0, right? If you subtract 1 from both sides, that tells you that x equals negative 1. So now let's cancel these common factors so we can find the y-coordinates of the whole. So we cancel x and cancel x plus 1 and x plus 1. So that will simplify to 2x times x minus 2. So I'm going to go to x equals 0. I'm going to plug that in. So that gives me 2 times 0 minus 2. So that's 0 times negative 2, which is 0. Okay, so that means we have one whole at 0, 0. And then we're going to find the other whole. Let's plug in. We have 2 times negative 1 minus 2. So that's 2 times negative 1 times negative 3. So that's negative 2 times negative 3, which is 6. So the next whole will be at negative 1, 6. Okay, so let's compare to the graph and make sure that we have two wholes, one at 0, 0, and one at negative 1, 6. So if you look at this graph, you can see that we have a hole here at 0, 0, and we also have one here at -1, 6. So now let's determine the holes of this function. So once again, we're going to factor everything. So we have x squared plus 5x minus 6. So we need two factors of -6 that are going to add up to 5. So 6 is negative, so we have a positive and a negative factor. 5 is positive, so I'm going to make the bigger factor positive. So I have 1 and 6, and then I have 2 and 3. And so -1 and 6 adds up to 5, so that's the correct combination. So I have x minus 1 times x plus 6. Now let's factor x squared minus x. The GCF is x, because I can factor an x out of both terms. So I have x times x squared over x minus x over x. And so when I do that, I have x times x squared over x is x minus x over x, which is 1. So now let's rewrite this function in factored form. So we have f of x equals x minus 1 times x plus 6 over x times x minus 1. So if you look here, you can see the common factor is this x minus 1. So we're going to set that equal to 0. So we have x minus 1 equals 0. You add 1 to both sides, and that tells you that x equals 1. So let's cancel this common factor, and that tells us that x plus 6 over x. So we're going to go ahead and plug in 1. Okay, so if we plug in 1, we get 1 plus 6 over 1, which equals 7 over 1, which equals 7. So 1, 7 is going to be the location of the hole of this function. You can verify it with a graph by going to Desmos and graphing the function. So now let's determine the hole of 5x squared plus 30x plus 40 over x squared plus 3x minus 4. So we're always going to start off by factoring the numerator and denominator. So let's go ahead and do that. So we have 5x squared plus 30x plus 40. Notice that these terms have a GCF, right? There's a GCF of 5, so I'm going to go ahead and factor that out. So I have 5x squared over 5 plus 30x over 5 plus 40 over 5. So when I do that, I have 5 times x squared plus 6x plus 8. So now I need two factors of 8 that are going to add up to 6. So 8 is positive and 6 is positive, so we're going to have two positive factors. So I can have 1 and 8, or 2 and 4. 1 and 8 add up to 9. 2 and 4 add up to 6, so that's going to be the correct pair. So the factored form of the numerator is 5 times x plus 2 times x plus 4. So now let's factor the denominator. Let's factor x squared plus 3x minus 4. Okay, so if we factor that -4, -4, well, that's negative, so we need a positive and a negative factor. 3 is positive, so we're going to make the bigger factor positive. So we have 1 and 4, and then we have 2 and 2. So when we add these together, we have 3 and we have 0. So when I write this in factored form, I have x minus 1 times x plus 4. So now let's go ahead and rewrite this f of x with all the factored form of the numerator and denominator. So we have 5 times x plus 2 times x plus 4 over x minus 1 times x plus 4. So notice that the common factor is here, right? This x plus 4 is the common factor. So we're going to find the hole by setting x plus 4 equal to 0 and then solving for x. So we have x equals -4. To find the y value, we're going to plug into f of x in its simplified form. So f of x is 5 times x plus 2 over x minus 1. So that is 5 times -4 plus 2 over -4 minus 1. So that is 5, well, actually I'm out of room, so I'm going to write on the next slide. 5 times -2 over, let's see, -4 minus 1 is -5. So we have -10 over -5, which equals +2. Okay, so the hole is going to occur at -4, 2, because that is the y coordinate we found when we factored the numerator and denominator. So now you can go ahead and pause the video and try this example on your own. So when you do this, you can factor the numerator into 2 times x plus 4 times x minus 4, right? Because it's x squared minus 16, and that is the difference of two squares. The denominator also factors into x plus 4 times x minus 4, so we actually have two common factors. Okay, so two common factors means two wholes. So one will be at x equals -4. The other will be at x equals 4. Interestingly enough, in this problem, when you simplify and you cancel the common factors, the function just equals 2. Okay, so the y-coordinate of both of these wholes will be at 2. So the wholes are at -4, 2, and 4, 2. So in summary, you can find wholes of rational functions because they exist at values of x that make both the numerator and denominator equal to 0. You can find the wholes by following these steps. Start off by factoring the numerator and denominator, look for common factors, and then find the x-coordinate of the whole or wholes by setting the common factor equal to 0 and solving for x. The y-coordinate can be found by plugging this x value into the simplified function that exists after canceling the common factors. Then remember to compare it with a graph. If you're doing it in Desmos, remember you need to click on the point to see that it's undefined.